After completing this lesson, you'll be able to achieve these objectives. Define what hashing is. Describe how hashing works when used in a digital signature. List examples of hashing functions. Describe common hashing attacks and the preventative measures. What is hashing? Hashing is the process of converting data of an arbitrary size to a unique value of a fixed size. Hashing has some important features that support cryptography. These features are alluded to in the definition. 1. The output value is a fixed length, which is determined by the hashing function or algorithm. Because the output value is always the same size for a given algorithm, the bad actor has no intelligence about the size of the input data. It could be a 12-character password or a 6-page document. The bad actor has no idea. 2. To avoid collisions, the output value is unique for every input value, just like a fingerprint is unique for every human being. This feature makes hashing very useful when you want to detect changes to data. For example, should someone tamper with an electronic document, even if it's a small change, when comparing the hash output of the original document with the output of the altered document, you'd see that the two outputs are completely different and be alerted to the tampering. And 3, hashing is non-reversible or goes only one way. This means that if you run the output value through the hashing function, you will not get the input value. You will get an output value of the original output value. This feature denies a bad actor the opportunity to use the output value to reverse engineer and calculate the input value. These 3 security features of hashing play an important role in cryptography, especially when generating a digital signature. Click on the underlined words for more information. Combining the security features of hashing with asymmetric cryptography can produce a digital signature. A digital signature serves a number of purposes. Digital signatures ensure the data integrity of the information signed, authenticate the person or thing that signed the information, and support non-repudiation. In the first step of the digital signing process, the information that needs to be signed is hashed. This produces an output hash value. In the second step, the asymmetric private signing key associated with the signer encrypts the output value using an asymmetric algorithm. This encrypted output value is called a digital signature. In the third step, the digital signature is attached to the information. Click on the underlined term for more information. In order to verify the signed information, you require the corresponding public verification key. But how do you verify that the key belongs to the signer? In asymmetric cryptography, public keys are written to certificates. Certificates are issued and signed by a certificate authority, CA. In addition to the public key, the certificate bears the owner's name. The verification certificate can be retrieved from a repository by the receiver, or it can be attached to the signed document. In the first step of the verification process, the receiver's application hashes the information, producing a new output value. In the second step, after verifying that the signer's verification certificate is valid, the public key decrypts, in other words, verifies, the digital signature. In the third step, the verifier compares the new output value to the original output value. If they are the same, then you know that the information has not changed. Because the public key successfully decrypted the digital signature, and because the name of the owner of that key is written in the certificate, you can confirm the authenticity of the signer. There are a number of popular hashing functions used in cryptographic operations. Common hash functions are Message Digest 5, MD5, and MD6, Secure Hashing Algorithm 1, SHA-1, SHA-2, and SHA-3, Microsoft LANman, and the NT LAN Manager, NTLM algorithm, Haval, and RIPE-MD. The fifth version of MD5 produces a 128-bit hash output. This function was widely used until weaknesses, primarily a susceptibility to collisions, were found. MD6 has supplanted MD5. Thereafter, SHA-1 became more popular, followed by SHA-2 and SHA-3. The SHA-1 function produces a 160-bit hash output, while SHA-2 is really a suite of hashtag algorithms. The suite contains SHA-224, SHA-256, SHA-384, and SHA-512. SHA-3 lets you decide the length of the output value. LANman was used by legacy Windows operating systems to store passwords. LANman uses the data encryption standard, DES, which was proven to be not secure and could be defeated by brute force attacks. NTLM succeeded LANman, followed by NTLM version 2. Outside of North America, Haval and RIPE-MD are popular hashing functions. A very common method that is used to crack hashing is a brute force attack. This means that the bad actor will try different input values until they produce the same value as the original hash output. If the attacker has no idea of the size of the input data, a brute force attack will have limited success. However, if the attacker knows something about the input value, they can eliminate those input values that don't apply. For example, if the input value is a password and the bad actor knows the password requirements, for example, that the minimum length is 10 characters and the maximum length is 20 characters, and that it must contain uppercase letters, lowercase letters, numbers, but no special characters, then they can drastically narrow down the scope of their attack. As another example, if the bad actor knew that the hash output was protecting a 4-number PIN using MD5, then they could try every conceivable combination until they arrived at the same hash output. A type of brute force attack is the birthday attack, which is based on the birthday paradox and exploits hashing functions that are known to produce collisions. If you are in a room with 183 people, there is a 50% chance one of them shares your birthday. However, if you wanted to have 50% chance of any 2 people sharing the same birthday, you would only need 23 people. This is the birthday paradox. For hashing functions, this means that it is much easier to find any 2 matches if you don't care which 2 they are. When attempting to crack a hashed password, the bad actor doesn't care if their input data matches the password, only that their input data produces the same hash output. This is because servers don't store user passwords. They store the hashes of those passwords. So if the bad actor can reproduce the hash output protecting Alice's password, they can log in as Alice. As noted earlier, a situation in which 2 or more input values produce the same output value is called a collision. The birthday attack exploits the mathematics behind the birthday problem in probability theory. The success of the birthday attack largely depends upon the higher likelihood of collisions being found between random attack attempts and a fixed degree of permutations. The best defense against a brute force attack is to ensure that the hash function supports an output that is long enough to be computationally infeasible to break. When hashing is used to protect passwords, increasing the length of the hash output value may not be enough if the function is susceptible to collisions. In order to protect the password hashes stored on computers, you can increase entropy through the process of key stretching. Click the underlined terms for more information. To understand the math of the birthday paradox, it may be easier to calculate the odds that no one shares a birthday and invert the results. Imagine that. As people enter a room, you ask them their birthdays. What's the chance that 2 people in that room share the same birthday? If one person enters the room, there is no chance that they share a birthday with anyone because there is no one else in the room. However, after a second person enters the room, there is a chance out of 365 that the 2 people now in the room share the same birthday. 365 is the denominator because there are 365 days in a year, omitting the leap year, or 365 possibilities. In other words, there is a 364 out of 365 chance that these two people will not share the same birthday. When the third person enters the room, they must avoid two birthdays. Thus, the chance that the third person will not share a birthday with the first or second person is 363 out of 365. To determine the probability that none of the three people in the room share a birthday, you must multiply the last result with this fraction. 0.9973 multiplied by 363 divided by 365. When the fourth person enters the room, they must avoid three birthdays. The last result, 0.9918, is multiplied by 362 divided by 365. If you advance ahead to the 23rd person entering the room, there are 23 days that you have to avoid. Therefore, a 343 divided by 365 chance of not sharing the same birthday. However, when you account for all the people in the room, 0.5243 multiplied by 343 divided by 365, the result is a surprising 0.4927. In other words, there's about a 49% chance that two people in a room of 23 people will not share the same birthday, or a 51% chance that they will.